Okay, now we'll get to using power series to solve ordinary differential equations. This will apply when 0 is an ordinary point, and then we're guaranteed for a second order differential equation, we're guaranteed two linearly independent particular solutions in the form of a power series centered at 0. So this right here is a power series centered at 0. What it means to find the solution then is to really find these C sub n's, these coefficients of the powers of x. Anyway, if that's what the power series is, its derivative, since it's a sum of powers of x, the derivative is the sum of the derivatives. That first derivative is break down the n, it's n minus 1. With that n there, the 0th term is 0, so we start the sum at 1. Take the next derivative, and it's 0 at both n equals 0 and n equals 1. So we can start that sum at 2. So what we're going to do is substitute in these terms here, y prime and y double prime, into the differential equation. Manipulate those sums, and then apply the identity property to find the coefficient. So let's see how that works. Here's our differential equation. Y double prime plus x squared y equals. And we're told to only solve through the x to the 9th term. And you need to know where to stop, because there's potentially an infinite number of coefficients in the power series, and you can't, if there's no pattern to it, you wouldn't be able to do that. So in the problem you'd be given, you'd be told when to stop. So if we characterize this solution, it's already in standard form. The p equals 0, the q equals x squared. So there's no singular point at all. So yes, 0 is an ordinary point. The radius of convergence is infinity. And the interval of convergence is the entire real line. Here's what we substitute in. Put in this sum for y double prime. That's the sum here. Plus x squared times this sum for y. So this right here, all we did was substitute in these terms up in the original equation. So let's start manipulating. So here's where we left off, and that equals 0. First thing we'll do, going from this line to this line, is bring in any terms in front of the sum. And in this case, that's this x squared. That would increase the power of this exponent, this x, by 2. Now, look at where each sum starts, what power of x. This one, when n equals 2, that's x to the 0. So this starts at x to the 0. At this one, n equals 0, that starts at x squared. They start at 2 different powers of x. We want to get the sums to sum over the same powers of x. So we'll pull out the first 2 terms of this guy. X to the 0 term and the x to the 1 term. Pull it out of this sum. So the n equals 2 term would be c sub 2. 2 times 1 times x to the 0. Then n equals 3 would have c sub 3 times 2 times x to the 1. Pull those 2 terms out. Now the sum that's remaining starts with n equals 4. And this guy was left alone. Now the 2 sums start at the same power of x. So now what we want to do is change the indices. And I'll change them from n's to k's. And the way I always do that, set my k equal to whatever this exponent is. So for this sum, I'm going to set my k to n minus 2. And that means n equals k plus 2. So every n here becomes a k plus 2. So C sub K plus 2, K plus 2, K plus 1, X to the K. And when N equals 4, K equals 2. So that sum starts there, K equals 2. I'll do the same kind of thing. This one, K equals N plus 2, so N equals K minus 2. Change those, I get this. And now you have both sums summing over the same indices. K equals 2 to infinity, same powers of X. I can combine these two sums. If I combine those two, this is what I have. After the manipulation of the sums, here's what I have. What I just went through is pretty important. Solve a lot of these, you're going to be doing this a lot of times. Now we can apply the identity property. Every coefficient of every power of X must be 0 for the whole thing to equal 0. This is the X to the 0 term, so it's got to be 0. This is the X to the 1 term, so it has to be 0. And this whole thing in brackets is the coefficient of every X to the K term for K equal 2 and up. So it has to be 0 for every K from 2 to infinity. I can express this relationship in recursive form, solving for the higher coefficient. Solve for C sub K plus 2 in terms of C to K minus 2. And this little recursive relationship applies to every K from 2 on up. And these two guys up here require that both C sub 2 and C sub 3 equal 0. This whole line here, what I'll call the recursive relationship. At that point, we can just crank out what all these coefficients are for as many as we want. Oh, and how do we do that? I didn't say anything about C sub 0 and C sub 1. I've got C sub 2s and up. Well, C0, C sub 0, and C sub 1 terms are always arbitrary. We can set them to what we want as long as we don't set them both simultaneously to 0. So to get two linearly independent solutions, I do what I call the 1001 trick. For one solution, I'll set C sub 0 to 1, C sub 1 to 0. The other, I'll do just the opposite. C sub 0 is 0, and C sub 1 is 1. Here's our recursive relationships. Let's do it for the first particular solution, where C sub 0 equals 1 and C1 equals 0. This first K is 2, so I'll be solving for K C sub 4. That equals minus C sub 0, which we're setting to 1, divided by 4 times 3. Our C sub 4 term. C2 and 3 were already 0. So I'll go to the next K, K equals 3. That will give me C sub 5. That equals minus C sub 1 over 5 times 4. But C sub 1 was 0, so that equals 0. You just keep doing this. I'm not going to go through all that arithmetic. Just keep doing the arithmetic, get a bunch of numbers until you get as high as you were told to go. Now you put all that together. For this particular solution, I call it Y sub 1. This, and now we just need to find those C sub n's. C sub 0 equals 1, C sub 1 equals 0, 2 and 3 equals 0. 4, we only have 3 non-zero terms up here. Generated them from this recursive relationship, and Here they are. Just write out the sum like this. Once we get to the highest term we need, we just put dot, dot, dot. Then for the second particular solution, the other 1, 0, 0, 1 term. This time C sub 0 is 0 and C sub 1 is 1. I'm not going to go through the arithmetic again, but again, we get 3 non-zero terms up through C sub 9. The x to the 1 term or C sub 1 term, C sub 5 term or the x to the 5th power, and the C sub 9 term or the x to the 9th power. We now have two particular solutions. You can write the general solution as a linear combination of those two particular solutions. You could write these and then just write that. And you do need these arbitrary constants for the general solution. They will depend on what your boundary conditions are. But we're not going to solve the boundary condition problems just yet. So that's a complete example of how to do it.